And just a very quick review to get us up to the part where we were before. We want to model GeoGrid. This is what GeoGrid looks like. And we want to have it inside of Pavement. Here's some GeoGrid getting laid down. Here's some old-fashioned before they had GeoGrid. Try to get a train to go across a swamp. And the basic idea here was that people in engineering practice who design pavements believe that GeoGrid allows them to make a base material that has less thickness with the same response. And this is the layer we're concerned with, this aggregate base layer. In order to do that, there was a big comprehensive research program, and it involved myself, and it involved Minnesota Department of Transportation, and it involved a number of people from the University of Minnesota, actually over about a 10-year period, with the goal being to understand how GeoGrid affects the aggregate base. This, in the end, is the way that this is the model that is used to design pavement in Minnesota. And what you have is an infinite half space with the traffic load, and this is an elastic analysis. And what you have are layers, and each layer has a thickness, a Young's modulus, and a Poisson ratio. And these are the failure mechanisms. Again, if you keep flexing this asphalt, it's like flexing a beam. You create tension in the bottom fiber, and as you keep on doing that, you get vertical cracks that begin to grow. Just like when you flex a paper clip multiple times, you get these vertical cracks at the micro level, and if you do it enough times, they can go all the way through, and then you get breakage. In the aggregate base at the bottom in the compacted soil, you get this localized failure, which then affects the deformation state up here, and you get these ruts in the roadway. Basically, the idea is this program has to get run because this program accounts for fatigue, for example, and if it accounts for the value of the trucks and how many trucks are going over and million loading cycles. And basically the idea is that you have to design it so that it'll last for at least 20 years. So our goal here was to just affect this parameter, E2, which is the modulus of the base layer. If we can increase that modulus by adding GeoGrid, that's going to reduce the thickness of the base that we need to have. So we wanted to understand what's the effect of GeoGrid on the modulus of the base layer. This is what happens when you take a triaxial cell. This is a big cell. This is about half a meter high, and you put the GeoGrid in there along with the ballast material. Forget about the GeoGrid. If you just take this thing and if you repeatedly apply a deviator stress, which means you have a constant confinement, and you just keep applying the axial load, axial strain actually, you get this hysteretic effect as you continue to do load cycles. Eventually you reach a point where the hysteresis loop stays the same. The idea is that that is the state of the roadway after, I don't know how long they think it takes, maybe months of loading. And then the thing just keeps on squeezing and unsqueezing in this linearly, not in this non-linearly elastic fashion. You take the slope of that, and they call that the resilient modulus. This is what you measure in the lab. This is what we're going to compute in PFC. We're going to use that as the value of E for the aggregate base layer. And so what we're concerned with is looking at what is the resilient modulus just for the aggregate, and what is the gain factor of the resilient modulus. It should be higher when there's GeoGrid in there. That's the goal of the modeling. This is simply a lot of words, but what it really says is a GeoGrid will result in a stiffer base. The idea being that the GeoGrid prevents lateral spreading, right? When you push on a big base of granite, think of a railroad. Everybody's seen a railroad track, and the railroad is built on ballast. There's a big pile of ballast, and the tracks are on top of that. And just think, when the train goes by, that ballast wants to spread out, lateral spreading. And putting in the GeoGrid, if it interlocks properly with the ballast, it's stiffer and it doesn't spread out as much. That's the idea. The first question is, well, why don't you just get field data? And the answer is yes, they can get field data, and they've got some field data, but at best it gives us a qualitative indication. So what they do, this is super cool. They do a falling weight deflectometer test. See this thing? this thing has a huge weight that's very heavy on it. And what they do is they basically drop that weight onto a roadway, and then they have little surface megaphones that record the wave, right? When I hit something, there's a compression wave, or actually a surface wave as well, that travels outwards, right? If you were on the table, on the end of a dinner table, and I was on the first end and I got excited and I pounded the table, your silverware would shake, right? So the same thing happens with the roadway. Based on that, those measurements, they're able to back calculate the stiffness of the system. So they do this, it's a non-destructive test. And what they did is they went, this is northern Minnesota. Lake Itasca is right over here. We've already talked about Lake Itasca. They went on some roadways, and part of these roadways, I think these were built about 10 years ago, and some stretches of roadway do have geogrid in them. And so what they did is they made a bunch of these measurements, and what they then did is they converted these stiffnesses to what they call effective granular equivalent, saying the stiffness is worth 3 inches of aggregate base, or the stiffness is worth, here we go, the stiffness that they measured is worth 31 inches of base. It's equivalent to that. And what they found, as you see here, this is all good news. It means that the parts that had geogrid were effectively stiffer. Okay. The problem with this data is that this was not a controlled thing. This was just a roads that were built 10 years ago, and people can say, well, in this region, maybe the soil is different, and maybe the soil itself is stiffer. And so it gives us qualitative indication. It makes us feel good. It says, hey, this is part of the reason why field engineers who design this believe geogrid is stiffer. So that puts us on the right track, but we'd also like to get some more confirmation of that. And so what we do is we did this, I call this thing the pavement design package in PFC. And here's, as we've said, we're going to measure the resilient modulus. We're going to do triaxial tests and measure the resilient modulus for both grid and no grid. We're going to try to set those things up so that we have sort of a typical, we're going to have the size distribution of a typical ballast as well when we do that. And then the whole idea, and this is what the client did, is he spent the whole entire summer doing parametric studies where he was running multiple instances of PFC, and he really thought this was exciting. He would run these things all evening, all night, and then he'd come back and he'd look at things. And of course, he varied all sorts of things, such as grain size distribution, moisture content, stuff like that. There we go. And then the whole idea is to use the field measurements, use whatever lab data they had, and use these runs to somehow figure out what those gain factors would be. And remember, MinPave is that model. That's the model that's embedded that we talked about with the layers. That's the model that's embedded in the design program that is used in Minnesota. Now let's start talking about a little bit of the physics of this system. What we have here is we have two things going on. These are the two grains that are pushing against each other. The surfaces are bearing against each other, so there's going to be a force. What I'm showing here is the force of grain 1 acting on grain 2. And what I'm also showing here is the idea of we have liquid suction. We have an unsaturated granular material with a small amount of moisture. That moisture sits because of surface tension, it sits between the grains, causes a suction. And so I'm trying to show this yellow. It's supposed to be my thing. It's sort of, think of it as honey, think of it as water. That suction then, again, acting on grain 2, the presence of the water is causing a suction force. So this is the system. We're going to handle the suction force. I'll talk about that a few slides away. But first, let's talk about how we handle the interaction force between the two surfaces. Okay. This is the super cool thing. We use a particular contact model called a Hertzian contact model. So who was Hertz? Hertz was a scientist in 1903, and Hertz said, I want to understand what is the interaction that occurs when two elastic bodies are pressed together. Okay. And he was a smart guy who knew all about theory of elasticity. And so, and I don't know if he was an engineer or a professor. I don't know that much about Hertz, but he decided to try to solve that problem. So if I asked you and said, how would you solve that problem? Two elastic bodies pressed together. Well, you would probably say I'd buy a finite element program and I would make an elastic body and another elastic body, and I would push them together and measure force displacement. That would be one way to do it. He didn't have finite element programs, of course, so he had theory of elasticity. And of course, the other thing you have to answer is, if you're going to press two surfaces together, what's the shape of the surfaces? And so he said, well, one of the shapes that I can handle in a general way, let's talk about radius of curvature. Any surface can be described locally as having a radius of curvature. And so he said, given body 1 and body 2, which are actually giant elastic bodies that are being pressed together, what is the force deformation response if you just push them directly together in the normal direction? And this is what he found. So what we're plotting here is overlap is going left, and this would be they're not touching. So of course, if they're not touching, there's no force. But if we start squeezing these two surfaces together, notice this very interesting effect. It gets stiffer and stiffer. And you actually could do this. I don't know, like I have my baseballs or even just two tennis balls. If you squeeze them together, you will notice that the more you squeeze them together, they're actually getting stiffer. And so this is the result of theory of elasticity with two enormous spherical bodies, each of which has a Young's modulus and Poisson ratio, and each of which has a radius of curvature. If the body's a giant sphere, the radius of curvature is the radius. Think of this as, and then this is a very small area over which they are pushing against each other. Think of this kind of like if you had the moon and the earth, and you slowly squeeze together the moon and the earth. Just think, there would be an overlap. There would be a disc-shaped area. It would be on the order of, hundreds of meters compared to the radius, which is enormous. That's the kind of scale you want to think about. But the same thing applies to any elastic body. So like a train, a big train that's pushing on a train track, the stress distribution, the behavior of that system is very well described by a Hertzian contact model. So it's like that. It's as though we have two elastic spheres pushing against each other. Okay. Now, he only was able to solve the problem for normal overlap, but now in reality also there's shear overlap. There's shear motion, I mean. And so then there was a guy named Mindland who was a professor in 1953, and he attacked that problem, and he actually solved that problem. And you get, I don't have the plot, but if this was shear force, you get a similar, it's not the same shape exactly, but it's a stiffening effect also in the shear direction. Okay. And so this is just, oh, here's my picture, right? It's like the earth and the moon touching, and there's my two tennis balls. And again, you see it's getting stiffer. There's my idea of the rail car and the steel. Now we can contrast the Hertzian model with another contact model, which we haven't discussed, but this is going to be our workhorse contact model. It's the simplest possible one. It's just a spring. It's just a linear spring. There you go, with a stiffness Kn. These are very different models. So the thing you would ask then is, well, which one should we use in our discrete element models? It turns out that you can do the vast majority of applications can be done quite nicely with a linear model. A linear model is going to run a little faster than a Hertzian model because a Hertzian model has to keep solving these equations. It's a closed form equation. It's not like you have to invert anything, but it's still a complicated equation that's a function of the radiuses and the moduluses of the two bodies. So the linear model works very good for just getting mixing and flow, granular flow type stuff. The Hertzian model is important, for example, if you actually want to model waves going through a bonded assembly of material. As you may know, if you have a box of sand or a sandstone, and if you do it, you put it in the lab and it's just sitting there as a cylinder and there's no confinement, you can smash the top and you can measure the wave speed. But then if you take it in a triaxial cell and you apply confinement, and you smash the top, you're going to find that the wave speed is going to increase. Okay. One way to get that in a discrete element model would be to use a Hertzian contact model, because when you squeeze it, now suddenly you're stiffer. And it's the stiffness is a key element that affects the wave speed. Stiffer material has a faster wave speed. Also, it's going to affect the resilient modulus, behavior, as we're going to find out. And so for this work, we decided to use a Hertzian model. So just to get the idea of the effect here, we built a couple of systems, looked like this. This one, these are spherical particles. This is a triaxial cell. We used two different size distributions. We gave them the modulus of granite, so that Young's modulus is around 70 GPa. We said that's kind of a typical aggregate base is going to be made of something similar to that. We do two size distributions. These guys are almost all the same shape. This is a much wider size distribution, as you can see, small guys and big guys. And then we ran a triaxial test at this confining pressure. And what we do is we apply a strain, 0.06% or 0.05. We basically squeeze it and unsqueeze it. And we trace out, we're measuring then the stress on that thing, the deviator stress. And as we squeeze it, we keep measuring how much the axial load is changing, right? So we actually get, oh, this is good. We're getting a hysteretic response. Notice the stress is still there when we're done, okay, because there's this nonlinear behavior that's happened. And what we find here, this is for the narrow grain size distribution. Here's our resilient modulus. Remember, that's the slope of this curve. So the Hertzian models is a little bit stiffer than the linear model. And with the broader grain size distribution, this effect is even more pronounced. So that's basically what we see in this. We're seeing that it does have an effect. The main reason it's stiffer, and let's just focus on the Hertzian model now, because that's the model we used. So the resilient modulus with a narrow grain size distribution, where they're almost all the same, is 207. But with a broader grain size distribution, it's bigger, it's stiffer. The reason it's really stiffer is not the Hertzian model so much. The main reason it's stiffer is that if you have a narrow grain size distribution, you get a certain porosity. But if you put a lot of small particles and big particles, they pack tighter and they get a lower porosity. And the porosity is a super important thing that's controlling that overall stiffness of the granular material. Keep that in mind, because we're going to find that that's going to affect what we do later on. This is the crude little picture of this idea of unsaturated soil mechanics. You get this suction between the grains because there are these liquid bridges that form, and it's a typical thing. It is a non-trivial thing. These are the typical suction that you're getting in an aggregate base, can go up to 60 kPa. And this whole process is extremely complicated. You could read for yourself. All these different things affect that. So we did not model directly a liquid bridge. What we did is we said, look, in the end, macroscopically, as far as the grains are concerned, they're suction. There are these contacts where there's suction. So let's put suction in. So here it is, moisture force. We just directly put in at every contact what the suction is. And so that then becomes this force here, right? Suction times area, assumed area of the contact, gives us a force that can be applied, okay? The other thing is that the sand, the small particles, the small part of the size distribution is neglected. We don't put that in our models. So here I've separated out the finer sand, the finer grains from the bigger grains. This is the typical, they call it a class 5 aggregate that's used in Minnesota. This is what's done in all discrete element modeling, because we just can't do that many particles. There's a huge number of particles when you start putting in the smaller ones. The effect of removing the fines, clearly there's an effect there. I've never seen any discrete element work that's actually addressed this and said what it is. People just immediately cut off the small particles in their size distribution, and they work with things that look like this, and then they, report results. So this is a big limitation of discrete element modeling. I just want to mention a thing. Now, how much this affects if we're building a synthetic sandstone and we're gluing it together, I don't know. Um, I really don't know. It might be that many sandstones, I'm going to speculate, have a much narrower size distribution, potentially because they've been sorted and things in the process. But I'm not sure. But we're doing the same thing. We just can't get all those fines in our model. Now, one additional thing we did to incorporate this effect of moisture is we expanded the interaction distance by which particles will interact. So what does that mean? Here's a system. Look at this particle. Notice they're in contact with three. So there's going to be three contacts. Remember, each of our contacts has a suction acting. What we can do is expand this radius, if you will, by delta. And then what we do is we find everybody that's within a distance of delta of this guy. So notice now there's two additional contacts that form. This is the idea being that it's the effect of that liquid bridges. So now there's 5 sites of suction acting instead of just 3. And what we find is that, and so this parameter we call the moisture gap. And what we find is that if we increase the moisture gap, right, the extent of suction increases, more suction, stiffer material modulus. Okay. This is a very also important parameter when we build bonded assemblies. And what we're going to find is, and so then that for a bonded assembly, we'd say, oh, there's an additional contact here and it's filled with cement. And so now there's also cement at a physical gap between the surfaces. And this has a huge impact on the triaxial response of a bonded system as well. If we put more cement in the system and if we fill cement in where they're not touching, it increases the modulus. It also increases the strength because this guy is much more connected and there's more sites that have to break than there is in this guy here. So that's a very important point. We're going to find that also when we build the sandstones, the pressure at which we pack the dry material before we put in cement is going to have the same effect. If I take this system and pack it tighter, there's going to be more contacts with this guy as well. Okay. So but for this application, this is a parameter then, moisture gap. Okay. And what we see, just look at this here, right? This is when there's no moisture. This is when there is moisture. We're happy because notice that when there's moisture, the system is stiffer. Okay. How do we model this geogrid? All right. We do have the ability now to have what we call structural elements when we have a geogrid structural element with a whole bunch of beams. That's part of FLAC 3D, and we can couple FLAC 3D with PFC now. We decided not to do that, and instead we said, let's just use PFC particles to represent the geogrid. And so essentially what we're doing is we're using this parallel bond model, which is I illustrated yesterday, the basic physics of it. These are glass spheres. The parallel bond is like cement between them. And so what we did here is we took this and we overlapped a whole bunch of these balls. Can you see it here? It's hard to see, but like this is thinner, smaller radius than this. And there's these protrusions here. And you can kind of see those bumps there. And it's thinner there. And so that's what we did here. This work was all done as an entire PhD study by a person in our German office who was an intern who actually got funded by a company called Tensar. Tensar makes geogrids. It's very interesting. So this is what Tensar makes, right? They're a very big international company. I remember sitting in the German office about 12 or so years ago, and the Tensar guy comes. He's the research scientist guy from Tensar, and he basically says our geogrid is better than all our competitors, but we somehow need to convince them that that's true. So could you build a model so that we could do that? And my first, of course, reaction was, well, whoa, let's not talk about the model. You need to convince me yourself. Why is it better? And basically, he believes it's better because his geogrid is much stiffer. And that's a key element of what's happening. It's much stiffer than the competitors. Therefore, it's more expensive than the competitors too. But he also gave all kinds of empirical examples where he showed like big giant swamps that are being they put all this grid down so that big trucks can drive on it and stuff. So Tensar funded this PhD guy, and he helped develop a lot of this methodology. In particular, what we took from all of his work was this little scheme whereby he glues these guys together, and using parallel bonds. And if you do that, what are you really doing? If you use parallel bonds between a string of particles, it's going to behave like a elastic beam of circular cross section, right? And here's my little illustration. This is one of those chains that you use to turn on your light bulb in the basement, and it's made up of all these little spherical guys with a little wire in between. And so essentially that's what we're doing. We're taking this system, we're putting cement in place of that wire, and what we're getting, this is a rubber gasket. We're getting a circular cross section beam that's elastic. Don't worry about this. And so that's what we're doing. So this is behaving elastically like the geogrid, and we're not going to be worried about the geogrid breaking. They're not going to break under the loading inside of a roadway. So this is what we did. We made a parameterized thing so that you could build these different shapes where we have a fundamental element that looks like this. You can reproduce those, in big patterns. This is just talking about how this thing behaves as a circular cross-section beam. So you can, bend this thing and let it go, and it'll go back to its original shape. There'll be no damage. So in this system, I'm drawing these circles here, these discs, to represent the cement, right? So that's what's giving us the structural response of a beam. And then, but those balls are all in there. And so those balls are the things that are going to come into contact with the other aggregate or with the other geogrid. And so that's what's happening here to get the actual grid-grid interaction or grid-grain interaction. It's the spherical balls that are going to give us that. Okay. So this is a way of making a string of spherical balls dance as though they were an elastic beam. Then, of course, the question is, this is a weird thing. If I had used a finite element, sorry, where is it? If I had used a finite element set of beams here to represent this, well, then my parameters of such a model would be the Young's modulus and Poisson ratio of the beam of this stuff, right? But that's not what we're doing. We're using this weird model with all these glued together parallel bonded materials. So the question then, of course, is how do you calibrate this? How do you choose these properties? Okay. And so we had to compare with something. So what we did is we compared with taking a rib and pulling it and doing this other thing, which I'll show you. So this is the simple test, right? We just built this sucker up. We just took this, fixed this guy, pulled on this guy, measured the force to pull, right? And so based on that, we were able to calibrate the stiffnesses of the parallel bond material to match the stiffness of the real system. Then we did this aperture stability modulus test. And what this is they take a grid like this and they clamp it into a steel fixture. And then they go here, and I'll just show you better. Look what they do. You see this? What they do is they put they're like metal nails on a plate, and then they rotate that plate, and they measure the force that's required to rotate, not the force, the moment required to rotate that. And they come up with the moment rotation stiffness, a rotational stiffness. So we did the same thing. We just simulated that in PFC. This looks pretty cool. Notice where we can do funky things in PFC. These are arrows at each ball, drawing the magnitude of the arrow relates to the magnitude, in this case, of displacement. And then they're also colored by the magnitude of displacement. All right, and we're going to learn how to do all that stuff with PFC. So we did this, and we matched the rotational stiffness of the actual geogrid. And we also did it for this type of grid, and we matched the rotational stiffness of this grid. Okay, then the question became, how do we pack that geogrid into the aggregate base, right? This is a complicated process. The best way to do this would have been to do it like they do in the real roadway, where you take a bunch of aggregate, you drop it under gravity, It sits there, it becomes an equilibrium, then you lay on a geogrid and you just let that sit there and go under gravity, and it sits there. Then you throw in some more aggregate on top and you let the whole system come to equilibrium. Just keep doing that. Okay. And then what you would do is compact it on the top with a bunch of vibration. They run these big machines and they compact each thing. You could directly simulate, you could directly model that in a discrete element model, and that would be the best possible way to model it. As we're going to find out, if you just take a collection of discrete element particles and let them fall into a box under gravity, it takes quite a long number of cycles until that thing finally comes to equilibrium. It's sort of like modeling a sand pile. If you threw sand in a pile, the reason it takes so long, think of a sand pile sitting in front of you on the desk. If you go somewhere near the bottom and just pluck out a few grains, you can potentially cause a global rearrangement of the sand pile. And what this is demonstrating is that small little perturbations anywhere in the system propagate through the whole other system and potentially make it rearrange. That's why it takes a lot of cycles to do this. We decided we didn't want to have to do all those simulation cycles just to build up our initial specimen. And so instead, I designed the following algorithm to obtain a packing with the geogrid. Very similar algorithm is used to obtain a packing of particles that are going to get cemented into a sandstone or any other bonded system. So you can see I'm telling you all this stuff because it's all useful stuff to understand in general. So here's the algorithm that I came up with. Imagine that first of all, there's no gravity. So we get to take a flight on the space shuttle and do this. So what we do is we take our region. This region here is going to end up, defining the shape. Okay. So we take the geogrid and we magically create it and we position it where we want it to position. And there's no gravity. So this model just sits there and cycles and nothing happens and it's not deformed. Then what we do is we generate a cloud of grains. In this case, these are spherical grains, and we generate them such that we randomly position them. And what we do is we say, if I happen to randomly position one that would actually be overlapping one of these grid balls, I don't use it. Okay. So what I get then is, and when I generate them, I say generate, keep going until you reach a certain number of balls, a certain actually porosity of balls. So you generate this cloud, but you basically delete all the guys that would have touched this. So now you've got this arbitrary, see the big overlaps of this system? Then what you do is you make all the surfaces of these particles have zero friction coefficient. And then you just cycle the model. But while you're cycling the model, you keep the geogrid fully fixed. All its velocities remain zero. And so what happens then is it packs itself, it rearranges itself. Notice the big overlaps. Notice there's no big overlaps anymore. It pushes itself out and goes into all the gaps and fills this thing tightly. Okay. Then what you do is you apply the confining pressure. This is going to end up being packed at a certain pressure. So now you apply confining pressure by using the walls to squeeze into this thing, and the geogrid is still not allowed to move. So basically, you make the cloud, you let it rearrange frictionlessly, then you go and squeeze it to the desired confining pressure that you want. And then what you do is you relax the constraint on the grid particles and you allow them to deform. And so now what you have is a locked in deformed set of things because I've basically applied some pressure on the aggregate and now you can see the shape. You can see the deformed shape. Okay. This is the algorithm we use. This is very, very fast to run this. For this toy model here with just, I don't know, there's probably 800 balls or something in 3D. This thing runs in like about 5 minutes. Okay. So we can obtain this packing. Okay. That's the way we did it. And now let's just look briefly at the response that we obtained. Okay. So here we're not using a cylindrical vessel. We're using a parallel pipehead vessel. And we're going to basically use the top walls to serve as loading platens. and we're going to use the sidewalls. They're going to have a servo mechanism that keeps adjusting their velocity so that they maintain a specified confining pressure. Okay. So we're going to build a model with no grid and a model with grid. See the blue? The grid is peeking through. This is what the grid looks like after it's deformed. Okay. And this first model we're going to look at is dry, so there's no moisture in there. Here we go. We take this thing, and after we have applied some compressive load to it, what are we seeing here? We're seeing these amazingly important things, these force chains. This is how the load is transferred and carried through the grain network. And some of them are pushing against the walls. See these two big guys? Those are two grains pushing very hard against that wall right there. Thickness of these lines is related to magnitude of the contact force. In addition, color is also denoting the magnitude of the contact force. And so these are the things that we see that naturally develop in a granular system, and they also naturally develop in a bonded system. This is actually that model now looking at just individually one of those grids. And what you're seeing here again is the same plot. These are the contact forces that are pushing against the grid. And so we can do this kind of stuff in PFC. Here I'm just looking at the forces, and I change the plotting visualization to say I only want to plot the forces acting on this guy. And so you can see they're squeezing really hard here. And you can see all this complicated force because remember, those big guys are pushing against these balls. As far as the model is concerned, these are just particles. Those yellow guys are particles. Two particles come together, boom, there's a contact, there's a force, okay? And this is then just looking at the cement. And so in here, compression is black and tension is red. And so what you see is that this cell right here is under tension. This guy's getting stretched. It's pretty neat. So you're getting this this interaction between the system and the grid then. And of course, since this has stiffness, it's getting pouring this way, right? That's holding the granular material in here it's causing tension here. That means the granular material there is feeling compression, right? So it's holding it in there. This is just a plot showing when I do the test, when I apply the strain, what I'm doing is I'm moving the bottom platen up and the top platen down. This is the displacement of the granular grains. Each arrow is at the centroid of each grain. And you can see how the top and bottom are being pushed, and the middle one's not doing much of anything, right? It's just sitting there because it's getting compressed from above and below. This is just now looking at the displacements of the grid itself. And again, basically the top grid is getting pushed down, the bottom grid's getting pushed up, and the middle one is getting a little bit of both going on. But, because it's basically in the middle there, okay? This is then showing the effect of moisture. So then here we can do the test, right? Apply an axial strain, squeeze it 1% strain, go back the other way, right? Notice the first thing, it's a hysteretic loop. So it's going nonlinear. Like this is kind of magic, right? Just like a granular material. It's going nonlinear. It gets out to here. Then we go and we push it back. And notice after we push it back, we don't go back to zero. So what we've done is we've squeezed it and unsqueezed it. And oh, look, there's still some stress on there. Now it's in a compressive state of stress. And again, what you're seeing here is the effect of everything. This is with no grid. This is with grid. With the grid, it's stiffer. And then the same effects of wet and dry. With the wetness, it's also a little bit stiffer. Here is a good one to talk about this business also. Now let's look at the black. That's no grid. Okay. Now what we're looking at is volumetric strain. Okay. And so what's happening, this is contraction. So we're applying a compressive strain, right? Up to 1%. We start squeezing this granular material. It starts reducing in volume, but then it reaches a point, oh wow, it starts dilating. Just like a granular material, it starts dilating and it goes up to here and then we unload. Notice what's happened at the end. I squeezed it, I unsqueezed it, and it's dilated and it's remained dilated. Okay. Again, just what happens in a granular material. Then if we put the grid in there, what's going to happen? is because it's applying that lateral constraint to the system, the dilation is inhibited. It doesn't occur until more strain has been applied. And you see the corresponding, and the final dilation is less because of the grid as well. Okay, so all this seems to mechanistically make sense. So we're happy with this. Then we said, let's apply this to an actual roadway. And so then we built in this box, we built a much bigger size system. You can see 250 millimeters approximately. These grains now are taken from a more realistic size distribution. This, the black lines, the black dotted and solid, this is the size distribution of what they call class 5 aggregate, which is a typical aggregate. This is the size distribution in red that we used. Again, notice grain size less than 5 millimeters. We don't have any of that in there. But this is what the system looks like. So here's a bigger chunk of grid. It's in the middle. We're going to squeeze this. We're going to apply confinement and squeezing. That's similar to what we believe would happen in a roadway. This is about 8,000 grains in this system here in 3D. Again, we don't have the fines. We try to account for the fines a little bit by having that moisture gap. So here then again, we go and we apply. This time it's a lot less strain that we apply. And this is a much more realistic model. This is the kind of models that he was running, not with just those simple balls with a small number of them that I was showing before, is like to demonstrate the general physics. So there you go, no grid, moist. Here's the measured resilient modulus. Then he looked at different effects of different parameters, right? So here, and this is what he did. He ran a resilient modulus test, right? Load, unload, and here's what it's doing as he keeps applying more strain and then cycling. And so the slope is the resilient modulus, and here the difference between the left and the right is that this was run at a higher confining stress than this one. And notice the red line is a steeper slope, which is what you would expect. Okay. This then, look at this axis here. This is porosity and this is measured resilient modulus. Now porosity is super important. So what we had to do is we had to somehow, when we made that packing, we have to do something so that we could control the final porosity of the packed system. And then once we do that, we can run tests with no grid at different porosities, and we can run tests with grid at different porosities. And it's only where you have the same porosity that you can compare the moduluses. Okay. So then the question becomes, how do we control the porosity? And what we did is, so remember, we took that system, we put the grains in just randomly overlapping. We let the friction be 0 and we let them readjust. Well, if you do that, you let them readjust when the friction is 0, you essentially create the densest possible packing. If you go and when you let them readjust, you use a non-zero friction coefficient, they're going to lock up at a less dense state. Okay. And so by running models where we varied the friction coefficient between 0 and the actual friction coefficient, we could obtain a series of initial states that had different porosity, that had less and less porosity. So we did that for the no grid case. We did the same scheme for the grid case. And then here, for example, you can look at the difference. Okay. This is again showing how, these systems there, friction is an important thing, right? And then we had to do that weirdness when they rearranged with friction. We had to do that because remember, we are not actually modeling the same physical process of compaction where you let them fall under gravity, run a machine on it and vibrate it, put on a grid, put more. We didn't do that. So we had to come up with this ad hoc way of controlling the porosity of the initial system. Okay. Then just quickly to show again the kinds of stuff you do with PFC, we modeled, this is called a dynamic cone penetrometer. It's a way that when they actually lay down the aggregate base, they can in situ measure the stiffness of this thing and the strength of this thing. So it's just a big heavy weight that gets dropped and they look at how far it goes in, right? So this is the tip of that cone penetrometer. This is a steel thing. It looks like this, right? So we said, oh God, we got to model that in PFC. So what we're going to do, oh, I'm not showing it. There it is. We're going to take a whole bunch of balls and overlap them. We're going to turn this thing into a clump. And remember, a clump, it never changes shape, and it behaves as a single rigid body, and it has a single mass. So I can actually drop this under gravity. Okay. And here's then what that thing looks like. And actually, we're not dropping this thing. We're forcing it. No, we are dropping it. Sorry. What we first have to do is take this thing and slowly push it down to a certain depth. So that's what we're doing here. We run the model, we force, this is penetration, this is versus time. So we force it to penetrate to a certain depth. Now we cycle, nothing happens. Then we go and we drop a hammer on it and it penetrates more and it stops. And we drop a hammer and it penetrates more and it stops. And so this is what that system looks like. And here we go as we start making these hammer drops. And again, the reason that this thing is getting resisted is because these forces are acting. These are the forces between the grains and between the grains and the clump. And so you can see here, there's a bigger set of the force network here, the big, thick guys that are resisting at the front there. Okay. Then we did the same thing, but this time we had grid in there. And so again, we force penetration to a certain depth. Nothing else happens. Then we drop the hammer, boom. Then we drop the hammer, boom. What the heck? What happened here? And what happened here, as we're going to see, is that this thing actually pushed against the grid itself. So these things are a sequence and they go from left to right to bottom to top. It's like a clockwise thing. And so here we go. This guy right there, see, he's starting to hit. He's starting to hit the grid on hammer drop 2. And then by the time hammer drop 3 occurs, he gets pushed back. Okay. So you're getting that natural interaction of this thing. And so again, in summary, noted we can do triaxial tests, dynamic cone, and we also do this lightweight deflectometer. Remember that thing that was dropped on the road by that big weight. I didn't show you that. But again, notice the model now. What are the things that we can vary? What are the parameters of the model, right? We can change the geometry of the grid. We can do triangular grid. We can do rectangular grid. We can change the stiffness of the grid, right? Which is the key parameter that Tensar believes is important to make their grid better. For the particles in there, for the ballast, right? We can change the shape of the ballast. I didn't show you this, but we could also, instead of creating spherical grains, we could create clumped grains with like 2 or 3 guys that overlap each other. So now they're not just spheres. We could do that. We obviously can control the size distribution. The other thing we specify, because we have that Hertzian model, is we specify the Young's modulus and Poisson ratio of the grain material itself. We could control the porosity and the packing, and as we change porosity after we get that packed system, everything's related to that, and then we could add moisture, right? So we could look at all those different things, right? And so again, we believe we have a mechanistically defensible model because our model is providing lateral restraint, and we have some confidence it's making sense because of some of the stuff I showed you as we got to this point, right? It's only once we know we have a mechanistically defensible model that we want to actually use it. So that was basically the research part that I was involved in and got it to the point where we believed it was all working. And then I essentially turned it over to our client. And then he's, as I said, spent the whole summer doing all these parameter studies running this thing. Okay. And so again, we can quantify the stuff, right? And we've already talked about this. These are the different things we study and look at their effects on stuff. This has been used then by my client. He did, based on all those runs and everything else, he then proposed a set of criteria whereby that modulus can be increased as a function of all these different things. And I don't know if that's in the program that's being used yet or not. And so remember, this is this talk, that was just an example. So here's my final set of conclusions that this is important. This is what I say based on all of my years of experience of doing discrete element modeling. So what do we have? What is PFC? It's very general purpose. to do distinct element modeling. And it can be used to simulate both granular and also solid, right? Solid materials bonded, they start to break apart, they become granular. So that means they can fracture, they can also flow. We're really typically looking at brittle materials, right? We have this idea of these bonds, they typically are brittle. But as you're going to see, we also now have bonds that can be more plastic-like. And really, it's a wide open thing because any type of discrete bodies, in terms of the bodies we have in PFC, spheres, clumps, or polyhedra, are going to interact in any way that they interact. As soon as, if you want them to interact, you create a contact. And then you can put in a law that says, knowing the properties of the two guys, we can figure out what the force is. And we're going to talk about how that's been used to model like magnetic effects, for example, force at a distance that can happen between things. And again, I'm just stressing here that ITASCA's primary expertise is in rock mechanics, and that ability to do rock mechanics work is typically embodied in this bonded particle scheme. All right, so we made it. End of the talk.